Hello and welcome to TidyX episode 158. TidyX is a screencast where we go through and explain how our code works. My name's Ellis Hughes.
My name's Patrick Ward. Thanks for checking in with us. TidyX 158. We're talking about package development, more specifically, package development when you have your own bespoke functions. We've worked our way up to the point where we are ready to show you how to put some vignettes into your package. So most good packages, you can do question mark and then the function name, and you're going to get some just short snippet, very specific examples to that function. But vignettes tend to be a bit more all-encompassing. They show how to use multiple functions, and really they show the intended way that the author of that package is thinking about how those functions may work in a productional way. Like, how would you operationalize these functions? So yeah, we're going to kick through the vignettes for our TidyX package, our TidyX Base package here. Ellis, how do we set up a vignette?
For sure. Yeah. So it's actually very simple. The use this package, as we've referenced through a number of times throughout this series, of course, has a helper function for allowing you to create new vignettes. And so that is the use underscore vignette function. And then what you enter into it is the name of the vignette file that you'd like to be creating. And so in our situation, what we did was using underscore TidyX base. There are some requirements as to what you can enter. You can't have spaces, you can't have numbers, it must be letters, and it must be a dash or an underscore. Those are the only viable things that you can add there. Once you run that function, we're not going to run it right here because we've already done it and we don't want to destroy all the work that we've just done or done to already create our vignette. But if you were to run this function, what'll happen is it'll create a vignettes folder inside of your R package. And so what you can see, if you go into files here, there's this vignettes folder created here. Then it creates the vignette RMD using the title that you passed in here. So if you click in vignettes, we have our using tidyxbase.rmd. And note, it's an RMD file. Then it's going to, because it's an RMD, we're going to need a way to actually compile our RMD, if we don't have that normally documented, into your description file. It's going to be adding in the dependency for you. So you can go and click in description here. And now we have nidr as one of the suggested packages, because that way you can always compile that vignette. And then finally, it's going to be adding a vignette builder entry into our description file. So it's got this vignette builder. Again, this is for when you're compiling the package. It's going to tell Crayon or whatever tool that you're using to compile your R packages what package to use to generate your vignettes for you. So of course we have the vignette, the .rmd vignette using underscore TidyX base created, and it's in our markdown. So at the very top, it's got that YAML. It's got the title that we entered using underscore TidyX base. It must be structured in that way. It's got the output. So what is the file output type that it's going to be knitting to? In our case, it's going to be our markdown HTML vignette. So it's going to be an HTML based document, but it's got some vignette flares around it, or vignette styling included with that. Then very importantly for vignettes is this vignette entry in the YAML file. And this is what's going to tell, once the vignette gets compiled, some meta information around it. And this is incredibly important for once the package is knitted and together and available, or not knit, compiled, for actually viewing the various vignettes that are included in your package. So as Patrick mentioned, if you have a good package, you likely have vignettes. The way as a user you can see them is you can go to their package down website, and they're going to be shown as the reports, I think, in the package down website. But if you're just using plain R here, or don't have internet for whatever reason, what world would that be? You have the vignette function inside of your inside of R, and so you can do vignette package equals whatever package name. In this case, we're going to do the Lawman package. You can run that, and it's going to create a little pop-up here. And so this is going to tell you, here's all the vignettes that are included inside of the Lawman package. So there's hits by type, strikeout, and home runs.
Home runs.
Strikeouts and home run. I can
Yeah.
read run scoring trends, payroll, and vignette intro. So an introduction to how the Lawman package works. The way that you'd go about actually opening up that specific vignette is you specify the topic. So note this is actually kind of the topic. So even though it's the title of the vignette, it's really the topic that you'll be accessing. And so in this case, we're going to be opening up the run scoring trends out of the Lawman package. So you can run that and that'll open it up in this viewing here. So Martin Monkman has added this vignette into the Lawman package to allow a different way that you can look at the data included in the Lawman package. So it's very powerful and very helpful for individuals to see how they might be able to use your R package and all the functions included in it together, as opposed to, again, as Patrick mentioned, much more specific, here's how this function works on its own. And then remember, if you're liking what we're talking about, you should definitely subscribe down below. Hit that subscribe button. So let's get into the actual vignette that we've now created, the using tidyxbase.rmd file. So that's just like any other RMD file, like functionally once you get past this piece here. Mm-hmm. So we've got at the beginning our setup chunks here. This is going to be setting the nidr chunks so that the code sets are collapsible, and any comments are going to have this marking there. The libraries we're going to use, so of course the TidyX Base package, which is this package, and the Tidyverse package. Now we made a rather simple choice to make a very simple vignette, just mainly showing code, not really adding a lot of text in our vignette. But we could, of course, go and write tons about how the beta distribution is to be used in this specific example, but we're choosing not to do that. But let's go through actually the code that we're including in our vignette. Patrick, do you want to get us started?
Yeah, so the first thing, remember that we're starting with the beta distribution, and that's going to require us to get some sort of population prior, so a population average and a variance. And because we have it already in the TidyX Base package, the data sets that we want to use, we simply have, we can simply call those. So the Lawman batting 2010 data set is already in there. And in order to set these population priors, we're just going to filter out some of the players that batted at a normal amount. And we're going to pull those batters into a vector and then get the mean of that. And then we're similarly going to do the same thing for the variance. So those are the two bits of information that we require here to get our functions to go. So now we have some information to go on, and we can continue on here with our vignette. We're going to pop the population average and variance into the get beta parameters function. That gets us the alpha and the beta for that observed population. Remember, this is empirically derived. So now we're ready to do the work and produce the plot for our vignette. So we're taking all of that Lawman batting 2010 data that we had. We're going to create a posterior batting average for every player using the posterior beta mu function, which we created within our package. And so we're going to specify the arguments there, which is the prior, information for the alpha and the beta parameters. N is the number of observations for a given batter, so how many times they have batted, and then successes in this case is going to be every time they got a hit. So that's what we're trying to look at here is batting average. Okay, and then we also create just a long column of population average because we're going to use that for plotting purposes. We actually didn't need to put that in there. We could have just specified it in the plot, but just to keep things simple. So into our ggplot we go. On the x-axis, we have our batting average, and on the y-axis, we have our posterior batting average. So we have our observed batting average for the player, and then we have the posterior batting average, which is the observed data, the observed batting average, inclusive of the prior data. So that's what we just calculated. We're going to do this by geom point, and we're going to make the size explicit to the number of at bats. So if you batted more, you get a bigger dot on the plot. We're going to set some lines here to give references. So we're going to set an H line at the y-intercept, which is going to be the population average, the population batting average, and then an AB line, which is going to be a line of equality. So that's a line with an intercept of 0 and a slope of 1. So if the posterior batting average is exactly the same as the observed batting average, it will lie directly on top of this line. And when we run this little couple lines of code there, we're going to get a plot that looks like
It's thinking.
it's trying. Uh-oh. It's still going.
Yeah, it's crunching through. We'll just move forward, and it'll pop up at some point while we're talking.
Oh, here it comes.
I think I had it zoomed in too far.
Yeah. You're lucky you didn't crash it. Sometimes when I do that, our studio crashes on me. It's like trying to think on a plot and I'm get excited and I try and, make it bigger or something. I don't know why, but it totally crashed.
We can try one more time.
Yeah, that was weird. All right, let's just leave it
there. We go.
There we go. Okay, so there we have our plot. So remember the observed batting average for the individual is on the x-axis. So we see a few guys over there all the way up at 1, meaning that they batted once. They have a small dot, so they batted once and they got a hit. We have a whole bunch of players down there at 0 who had some at bats and never got hits. And then we see that the more that a player batted, the larger the dot and the closer they are to that green line. They're getting pulled toward that green line. Similarly, for example, the guys all the way to the right that have a 1, you can see that their posterior, once we combine the prior information, which is the league average, you can see that their posterior is right around 257 or 260, something like that. So it's like a little better than average, but we're certainly not saying that they're 100% hitters, that they're never going to get out. So this plot just kind of shows us the way in which the prior information and the observed information are combined to reflect some sort of posterior determination of that player's batting average. The next example that we have is just going to be another way of kind of expressing the uncertainty around the player's batting average. So we're going to set a seed because we're going to take a random sample of players and we're going to randomly sample 10 players. And we're going to use our functions that we created to get the posterior beta distribution mu, mean, and the posterior batting standard deviation. So both of those functions we talked about in the previous episode. So here we can see we have a good kind of smattering of players. We have some players that batted a whole lot. We have a player that batted 0 times, so they have a nan for their batting average, but we can still make some sort of estimate. We say, well, they've never batted, so our best estimate in this case is that they're average until we see, further detail, until proven guilty, innocent until proven guilty, type of thing. And so you can see some players are pooled more towards the average than others. The individual with 644 at bats, his posterior batting average is like 0.259. We're not rounding up, it's 0.26, which is nearly exact to his batting average, and that's better than league average.
Yep.
So when we plot this, we're going to use the average and the standard deviation here in order to make some error bars. So we're going to take those players that we just sampled out. We're going to use coalesce here because I don't want that nan, but I do want to retain the fact that this person has a batting average of 0. So I'm just going to give it a 0 if there's a missing value. That's what I'm using coalesce for. And then we're going to do a player ID, year ID, so that we know what year the player batted in, because players could have multiple years. For example, Burner Co 01 is in there twice. Then we're going to do some ggplot here. We've got batting average on the x-axis and player ID on the y-axis. Again, the size of the dot is going to be based on their at-bats. And then we're going to use our error bars with the posterior batting average and the error bar for 1 standard deviation. Width of 0 means that we don't want the ends. So we don't want the Star Wars fighter pilot looking things. Size is 1.1, so we want it a little bit thicker. And then geome point here is going to be for the posterior batting average. We're going to throw that onto the plot. We're going to put it in red. So this is assumed to be their Bayes adjusted batting average. We're going to put it in red. And what we get is a nice looking plot like this, where we can see, for example, Springer 01, the Bayes adjusted, the red dot is nearly on top of the black dot because he's had so many observations that the prior information has generally washed out, and we're pretty confident this guy is better than average. Similarly, all the players that have zero batting average, we could see down, they have zero all the way on the left side of the plot, little dots, they've barely batted. Our best estimate for those guys is that they're probably right around league average. And also, we have much larger uncertainty. Notice Springer, the second one from the top, has a much tinier level of uncertainty because we saw him bat 600 plus times relative to the individual above him who maybe has batted only once or twice. We have a lot of uncertainty. We don't really know anything about that player. Yep. So that's a little bit about the beta distribution vignette.
Yep. And so it's nice for us to include all of this in the vignette. So you have all of this contextual information. So if you're doing something, you're using TidyX Base and you want to do your own analysis using data that has a beta distribution, you can do it yourself. You can just slot in. We've got a bunch of code here, not just showing how you might use or might calculate the alpha and beta priors, but also how you can actually apply this and different plots that you might want to generate. And so it gives us as authors the opportunity, authors of the package, the opportunity to impart to you ways that we might think that it could be used. And then you can just take this code, apply it to a different data set if it's reasonable, and do your own thing. And so the same sort of idea holds for the gamma distribution, where we're going to be pulling in. This time we're going to use the same data set that we did in the past for the gamma distribution, which is team runs, or the amount of times they score on average across a season. So we pull in the Laman team runs from 2010. We calculate the runs per game and calculate the average runs per game and the variance in that. We get the gamma parameters based off that to get the priors. And so we've got our alpha and beta values for the gamma distribution. We've got a prior of 8.3.4 or 83.4 and a beta prior of 18.8. We can then apply the posterior gamma mu and posterior gamma SD to calculate for every team what we think their actual RPG or runs per game average and standard deviation would be for every team included. And so we get this value here across all the different years. So like for 2010, Arizona, they had an average a runs per game of like 4.4. We said, yeah, that's probably pretty close. But then maybe like 2010 in Baltimore, they had 3.78. Like, yeah, maybe they're more like a 3.85 team.
Not a lot of movement here because everybody plays the same number of games. It's generally like what you see is what you get. This isn't like at bats. So could probably find a better example than this, maybe like home runs per game or something like that.
Or look at it from a more apply this data set to this year.
Yeah.
Like I mean, I guess this year's almost done at this point.
Wow.
Considering it's September. But you could apply it to in the beginning of the season and go, okay, what would we expect our team to end up looking like?
Updated after every game. Exactly.
Yeah, and so that would be a way that you could apply this sort of data set, or these functions and what we've done so far. We could do a little cable there of the top 6 teams, or the first 6 teams, not the top 6 teams. And then, showing you how you might be able to generate a plot to visualize this. We're going to take this, the team posterior data set. We're going to calculate the difference between runs per game and what the gamma distribution says they should be getting. We do a geom plot to generate a histogram, or we set the aesthetic so X is diff. Make a geom histogram where the color is going to be black, but the fill is going to be light gray. So it's going to have like a nice outline there of black. And we're going to set a V line, so a vertical line of 0. So if you're exactly on, if the posterior is exactly the same as runs per game, you're going to be closer to that. And then we'd expect a nice tail out of that. And so we can look and view that. And what do you know? It does it.
Yay.
The math works. Who'd have thought?
Yeah.
And that's one way to visualize this. Then, of course, you can go and do another thing where you're going to look at just a scatter plot. So again, ggplot2, the x-axis is going to be the posterior. The y-axis is going to be the actual We're going to generate a genome point where the size are standard 3.5. I'm going to be using a shape with the ID 21, which I don't remember what that is off the top of my head.
It's going to be it's a filled in circle. So it's a
Filled in
circle that
circle.
you can fill with whatever color you want. Yeah.
So we'll fill it to be gray, but the outline will be black. And then we'll set an AB line, again, of equality, intercept 0, slope of 1. We're going to color that red and size of 2. So we're going to run that. Bada bing, bada boom. So you can see, teams over here. So this is, runs per game on the y-axis, posterior. Yeah. So I'm trying to remember, are these doing better or worse than?
Yeah. So so through on the left side of the plot, the posterior runs per game tended to be higher than the observed runs per game. So basically, those teams scored less than we would have thought. Mm-hmm. And the flip is on the opposite side. And then in the middle, it does pretty well. And really, what this shows us is, again, everybody plays the same number of games, but this really shows us that, the idea of regression to the mean, because next season you might expect that some of the teams on the bottom probably regress up a little bit and play closer to the middle, and the teams on the top might regress down a little bit and play closer to the middle. And this is how regression to the mean works. So in the tails here, we see the inverse of on one side of what's taking place on the other side.
Mm-hmm. Of course. Thanks for putting words to my slow brain right now. But yeah, so that is another way how you might apply the gamma distribution. And so again, it's giving people here's plots that you might want to use to visualize this, not just using the functions themselves purely, and you must know exactly how you might want to visualize this, but we're giving you now the tools that you might want to use to visualize this sort of content as well.
Yeah.
And that's the purpose of a vignette.
Yep.
And cool. So with that, I think we're going to end episode 158. We're almost done with this series. Leave a comment down below of anything you would like to see us talk about when we're talking about building in our package, and things that have confused you, things you'd like to have us talk about, because this is really for you, to help you understand what's going on here. And we love talking about it, clearly. So with that, Patrick, do you have anything else to say?
No, that's about it. That's episode 158.
All right. As always, my name's Ellis Hughes. You can find me on various social media sites at Ellis_Hughes.
My name's Patrick Ward. You can find me on X at OSPPatrick. At Tidy_Explained is where the screencast lives on X. Tidy.explained@gmail.com is where you can email us. But as Ellis said, like and subscribe on the YouTube channel. Questions, comments down below. Easiest way to get in touch with us. Easiest way to get us to answer your questions. Easiest way to potentially have one of your questions become a future episode. And as always, we do have a Patreon page. If you enjoy the work and you feel like it's helped you in your work and been impactful in some way, and you'd like to contribute to our work, we are very gracious of that.
Thank you all so much, and keep on exploring your world.